Hello, and welcome back to AP Environmental Science. Today I want to talk about species interactions. And we're going to start that conversation by talking about what kind of species interactions there are. Basically, we're going to divide them into a couple of categories: competitive relationships, predatory relationships, and then the symbiotic relationships: parasitism, mutualism, and commensalism. And I've put this chart in here so you can kind of see you've got the two species that are interacting together, and then who benefits and who's harmed or who is unaffected, right? And remember, parasitism, mutualism, and commensalism are all symbiotic relationships, and I'll define that in just a second. So really we're looking at competition, predation, symbiosis. Okay, so here's your first question. Sheep will graze grass down to the ground, which is not damaging in grasses that grow from runners or extensions of root systems. Which of the following terms would best describe this plant-herbivore interaction? So here's the thing. This is actually not damaging to the grasses. So it might be really tempting to say that this is actually some sort of symbiotic relationship because maybe as the grass is grazed, it actually helps it grow, and one could argue that that happens sometimes. But here's the bottom line. The sheep are eating the grass, and that makes this a predatory relationship. So herbivores actually are plant predators. Now, when we talk about predators, we're not really specifically talking about herbivores most of the time. But the definition of predation is when one organism feeds on another. The predator always benefits, right? And it will evolve methods for capturing prey. The prey is always harmed, so it's going to evolve ways to not get eaten, defense mechanisms. So you end up getting this sort of arms race where predators always have to be one step ahead of the prey, and the prey always has to be one step ahead of the predator. And that actually is called coevolution. So some big predator strategies are ambushing, right? You hide and wait. You can stalk. You can chase, you can do pack hunting like wolves do, and you'll also have weapons to go with those hunting strategies, right? So if you take that pack hunter, the wolf, who stalks and chases and has some pretty formidable weapons, you have quite the predator there, right? So to counter this, prey strategies include being too big to be eaten. By the same token, this is also a predatory strategy. If you're really big, you can eat anything, right? So think like crocodiles, lions, tigers. They're really big. They can eat lots of things. But an elephant, by the same token, is really hard to eat because it's so big. The other thing is you can be really tiny. You can be able to change your size. Think about pufferfish. You want to be just as fast and just as agile. Actually, you want to be more fast and more agile than predators. So that's both a predator and prey strategy. Prey need to have weapons too, right? They want to have claws and teeth and horns and spines and thorns and things. And armor like shells and plates and all of those. That's a really important thing too. Sometimes you're going to have something that would be, say, like a shell with spines on it, and maybe those spines have chemical defenses in them, toxins, offensive smells and tastes. And coloration is really important too. A good prey strategy is to either blend into your surroundings, be camouflaged, or to really advertise that you are poisonous or you are going to be a problem, and that is called aposematic coloration. That's the really bright coloration that you see in ladybugs or poison dart frogs or things like that. So what you'll have in this dynamics, and this is a little bit of a review when we're talking about populations, but just to remember, it's predation that causes those boom and bust cycles. When the predator population goes up, the prey population goes down. When the prey population goes up, the predator population goes up. All right, moving on to the second one. And by the way, we could spend the entire year talking about all these species interactions. We're doing just a really quick overview. So competition is the driving force behind evolution. This is the second driving force behind evolution, right? So we talked a little bit about coevolution, we were talking about predation. Now with competition, you have species that are trying to use the same resources, and you have two kinds of competition. You've got intra-specific, where you're competing with individuals of the same species, and then different species can compete for the same resources, and that's interspecific competition. It does not necessarily involve contact, and the interaction may only be because you're affecting the resources and you're limiting that resource for another species. So you can get this indirect competition too. But the bottom line is this: no two organisms can occupy the same niche, which is the principle of competitive exclusion. And so this is where you have competition, is when species are trying to occupy the same niche. They're trying to exploit the same food resource, they're trying to live in the same habitat, right? All of those are part of the niche, because remember, the niche is the role the species plays in the ecosystem. Okay, now two big ways to get over competitive exclusion, right, are resource partitioning and character displacement, right? This is how you stop competition, is you shift to another resource, or you use the same resource in a different way. All right, so the only time you have an alleviation of competition is where you have no region of niche overlap, right? So this question: certain night active moths and day active birds are specialized nectar feeders. They are exploiting the same food source. So how do these species coexist if they are in competition? Since both use nectar, eventually one of the two species will need to move to a new area or will become extinct, right? They do not compete for the nectar because they feed at different times of day. There's enough nectar to supply both the birds and the moths, so they're actually not in competition. Eventually the niche breadth will increase and there will be less competition, or none of these. Well, this is an example of resource partitioning, and the answer is 2. They're actually not competing for the nectar because they're not exploiting it at the same time. There is enough nectar, but only if they are splitting the time. So this is resource partitioning. All right, so when you are partitioning resources, you can do that either temporally, like we saw with the birds and the moths, right? That you are changing the time at which you access those resources. And you can also do it spatially. And spatially, a really good example of that are birds at a bird feeder or birds in a tree. And so here you'll have different birds. At the feeder, you actually get both temporal and spatial resource partitioning, because some birds feed at the feeder, some birds feed at the ground, some birds feed early in the morning, some birds feed later in the morning, some birds feed in the late afternoon, some in the evening. So that you get both of that. With the trees, you'll actually have some birds nest at the very top, some on the outside down to the middle, right? And then you'll have some inside of that. And so you just get all these different ranges within the tree, resource partitioning. Now, character displacement is where you end up actually accessing a different resource because you have some physical characteristic that allows you to do that. And an example of this is Darwin's finches. They all arise from the same mainland species, but when they get to the Galapagos Islands, there's so many available niches that slight variations in the populations mean that certain individuals are able to exploit different types of seeds or different food sources, maybe some insects, maybe cactus or whatever. And over time, you get populations building up around those food sources, and you get new species. So this is a big route to speciation. Okay, so here's your next question. A person breeds rabbits in a cage. After a few generations, she observes that the rabbits are more aggressive towards each other, the young are less healthy, and more rabbits die. This population is under stress, under the carrying capacity, density independent, or both under stress and density independent. So the answer to this is actually under stress. But one of the things that we want to know is, and they're clearly over carrying capacity, by the way, and that's what puts them under stress. They are not density independent. So what we want to talk about now is that competition is actually a density dependent factor. You only have competition when you have certain levels of populations, right? And so when we're talking about competing for space, think about it in terms of being on a train, right? If you are having just a few people on a train, that's great. There's lots of space. Everybody can spread out. But what if you have a situation that looks like this? This is extremely stressful. People will start fighting for space, right? This is the idea that the more actors, the more participants are going to make the share of the resource smaller, and this is why competition is a density dependent factor. Supply and demand is essentially what we're talking about. Now, intra-specific competition is actually about a couple of things. In its basic form, you're talking about food, right? You are in competition with others, individuals of your species for food, but we're going to see the most impact on the individuals from mate selection. And this is where you can talk about sexual selection as opposed to natural selection. So we're going to see intraspecific competition most heavily in mate selection, dominance, and territoriality. And occasionally, this kind of intraspecific competition leads to cannibalism, right? And that's sort of less fun. But mate selection and dominance are all about securing mates and securing territory, and territory is about securing resources. Okay, so let's switch to symbiosis. 3 types of symbiosis that we are going to talk about are parasitism, mutualism, and commensalism. And parasitism is something you're probably familiar with, actually, because tapeworms, ticks, those are all parasites, right? One species feeds on a part of another organism and relies on it to survive. In mutualism, 2 species interact in a way that is benefiting to both of them, right? So everybody wins. And then in commensalism, you have an interaction that benefits one species but has little, if any, effect on the other species. This is actually something that many biologists feel is not a genuine kind of symbiotic relationship. And so commensalism, oh, that should have an S in it. Hold on. Look, it's the magic of the digital age. Now there's an S in it. Okay. So commensalism, like I was saying, many biologists really feel like anytime you have 2 species interacting, there is going to be an effect on the other species, right? So one may benefit, and then the other one is either benefited or harmed a little bit in some way. And so it's never like no effect, it's just a negligible effect is kind of what we're looking at. Okay, so going back to that grass grazing questions, right? Some grasses actually benefit from being grazed, right? They get trimmed and it's good for them. So think about pruning if you're a gardener. Which of the following terms would best describe this plant-herbivore interaction? Well, if the grass benefits, right, it's mutualism. So this is a mutualistic relationship. Both the predator, who gets to eat the food, and the plant, who grows better, win. Okay, I'm going to start with parasites though, because this is, again, probably the one that you're most familiar with. Here's the catch about parasites. They do harm their host, but it's not in their best interest to actually kill them, at least not quickly in any respect. By the way, this is the grossest parasite that I could ever find, and I put a link in here, or one of the grossest, actually. There's other ones too. I put a link in here for you to see, because this is also an interesting connection to overfishing. So go ahead and check out that link so you can see what I'm talking about there. This is in your PowerPoint version of this. Okay, so essentially this little guy here eats away this fish's tongue and then lives in its mouth and eats the food that it eats. Gross. All right, so there's some gross ones. There are endoparasites and there are ectoparasites. Endoparasites live inside the host. Ectoparasites live outside the host on the surface. Okay. Now, mutualism is a win-win relationship. This is obviously the kind of relationship that we like best, right? Rhinoceros get parasites picked off of them. The little birds get to eat food, right? These birds are called oxpeckers, by the way. Same thing, clownfish and anemone, right? The clownfish get to eat stuff, right? And the sea anemone protects the clownfish. The fungi and bacteria that live in the roots of various plants, this happens to be a juniper, but in various plants, actually provide the plant with food, and they themselves get resources from the plant. All right, now, commensalism, Again, I told you it's little or no effect, and a good example of that are the bromeliads that live in high up in the trees in rainforest areas. These guys actually anchor into the tree. They do have a little minor effect on the tree, but it's not a huge effect, and so the tree is fine. And then these guys get closer to the sun, they get more rain. It's very exciting for them. All right. So let's shift over a little bit and talk about natural selection and evolution, because it is these relationships that are the heart of natural selection and causing populations to evolve, right? Remember, evolution is a change in the allele frequency of a population. And so if you have pressures, selective pressures, they're going to push certain traits to be more prevalent in the population. And so natural selection is based on, and this should be a review for you, by the way. Natural selection is based on two key observations. One, organisms generally have more offspring than can survive to adulthood. And here you're looking at the Christmas crab migration. Yay. And two, that the offspring are not identical. There's variation in their appearance, size, and other characteristics, and pressures can act on that variation. So, which is the best statement to describe the following inference? Those organisms that are better adapted to their environment have a greater likelihood of surviving to adulthood and passing these characteristics on to their offspring. Is it survival of the fittest, competition, fitness, adaptive traits, or survival of the fit enough? Well, for those of you that have had me before, you know that I actually call this survival of the fit enough. Lots of people call this survival of the fittest, but the answer is actually survival of the fit enough. You only have to survive long enough to have babies to pass on your genes, right? And that is considered success, and that keeps your alleles in the population. So how does natural selection exactly work? I'm going to do this with resistance to antibacterial soap, because this is a big issue right now, and it goes along with some of the other conversations that we've been having about our impact on other species. So this is kind of an unintended selection sort of deal. But basically, you start out with all these little bacteria here. They are not resistant, and they grow. But then a mutation happens, right? And so now you have a bacteria that is resistant, right? So you're doing your regular thing and you're cleaning up all the little bacteria, and that's super exciting, right? And so you kill them all. Or do you? Right? Because remember, some of them are resistant. And so in that third generation, the resistant ones and the regular ones that didn't actually die when you use your antibacterial soap, because remember, it only kills like 99.9 or whatever percent. They are going to multiply. Well, you're going to come and you're going to do it again, right? You're going to clean again. But this time, the ones who are resistant, they are going to stay. They are not going to get killed. And so over time, you're going to see this shift to resistant bacteria from not resistant bacteria. Right? And so what you end up with are these superbugs that you've probably heard about in the news, right? So this example that I just used of the superbugs is very much like what that happens with something else we've talked about. Well, in this case, it's the overuse of pesticides. Remember, we talked about using lots of pesticides has been creating superbugs and super weeds and things like that. It's the exact same process. Okay, now let's shift a little bit and talk about how do we get new species. Well, natural selection can actually cause populations to diverge. This is divergent evolution. Divergence can lead to new species. So for example, if you had a cute little bunny, right? And that bunny's population spread because it's a great generalist and it does all sorts of wonderful things, and it can survive lots of different environments. So some of them move really far north and some of them move really far south where it's hot. And so over time, you might get a situation where you get mutations that give you new traits, and the environment acts on existing traits already in the population. And over many generations, perhaps you get new species, this European cottontail, maybe you get snowshoe or Arctic hare, and down here you have a Texas jackrabbit. Right? So this is perfectly adapted for desert-like conditions, scrub-brush conditions. This little guy is perfectly adapted to the cold, snowy, seasonally changing conditions. Okay. So now what happens when you have natural selection and species don't have the traits to allow them to survive. This is where you get extinction. And there are two big kinds of extinction. There's background extinction. It's on average about 10 species a year. And this is normal, right? This is a normal thing. Species go extinct. They just are failed experiments, if you will, right? Now, there have been 5 mass extinctions where you have lost the majority of species on the planet. This includes that Cretaceous event 65 million years ago that resulted in the loss of dinosaurs and the rise of mammals. So sometimes mass extinctions are good for some species, and they're bad for the ones that go extinct, like, oh, boo, dinosaurs, yay, mammals, right? So that's kind of exciting. The question that we want to ask in terms of this class is, are we in a mass extinction now? And it turns out that we're losing way over the background number, right, for species. And so people are actually starting to talk about we may be in a mass extinction now, except the difference between this extinction and the last 5. The last 5 were caused by massive climate change, right? I've told you that climate change is a natural thing. Our question is it a natural cycle now, or is it something different? But by and large, mostly catastrophic events occurred and caused rapid climate change, and that caused huge problems. That is not what's happening now. It looks like if we are in a mass extinction, it's caused just by us being us. And that's something we're going to be talking about, and we've talked about already, and we'll be talking about throughout the rest of the unit. Okay, so let's shift gears. We've talked about natural selection. We talked a little bit about sexual selection. The third type of selection is artificial selection, and we have actually talked about this a lot without you realizing it. So what is artificial selection? Artificial selection is the gradual improvement of animal and plant characteristics through traditional breeding or genetic engineering over time for man's benefit. But really, when we talk about artificial selection, the bulk of the artificial selection that we've done is about traditional breeding. This bunny, I like this bunny because it's super fuzzy and cute. I like this other bunny because it's really little, so I'm going to breed them together to see if I can get a super cute, fuzzy teacup bunny, and it's going to be awesome. That is artificial selection, and we have done it with things mostly because we want them to work for us, right? Like we turned teosinte into corn because it is better for us. It's a better crop. We turned this turkey into that turkey, which is a delicious turkey, right? Sometimes we do it just because we can. We turned this pigeon into that pigeon, and that pigeon and those pigeons, and none of those pigeons can actually fly well. They're all weird pigeons, but somebody out there loves a pigeon that looks like that. So mostly it's traits that we find desirable for functional reasons, but anymore, a lot of times, it's just because we like it. Teacup, fuzzy bunnies is what I'm saying. All right, so that is it for this conversation. Thank you for listening. Please make sure to ask any questions that you have. A lot of this was a review, but even still, please ask any questions that you have at the beginning of class next time, and thanks for listening.